Hello dear students, my name is Vikram Nalode. I am an assistant professor in the Department of Mechanical Engineering. I am working at SATQI, Yadra, Uttarakhand. Today we will cover a very important point of an automobile. We will discuss about engine performances. So let's start today's lecture with the content. So in today's lecture we will discuss the objective of today's lecture and the engine performances, in which we will cover different parameters and losses. So let's start with the objective. Today's lecture's objective is to study and understand the performance curve. So let's start today's video lecture. So what is the engine performance? Generally, engine performance of an engine, it means that how its output varies over the entire range of its operation. So whatever the operations are carried out, then what output we are obtaining. So that is most important. So to understand, so we have to consider some of the variables. Those important we have picked, that speed, load, air-field ratio, and mean effective pressure. These are the important variables we'll consider while study of engine performance. When we are studying the performance, no doubt we have to understand what different types of losses are in the engine. So first we will consider that is due to ignition not being instantaneous. Generally, as the ignition of the charge in an actual engine does not occur instantaneously, as assumed in a theoretical air cycle, and is spread over a definite interval of time, a loss in power occurs because of the rounding of the peak. So this loss is shown in this graphical representation, pressure versus volume graph. The loss is shown here, and this shape change of pressure volume diagram depends upon the instant at which the ignition occurs. So that is represented in this PV diagram, variation of PV diagram due to the advancing or retarding of the ignition. So diagram 1 is the optimum curve when ignition takes place at point O. When however ignition takes place earlier than the optimum, this diagram 2 is obtained. Likewise, the shape 3 is also obtained. This shape 3 is obtained in case of ignition occurring later than the optimum. So accordingly, the change in the area of pressure volume diagram and hence the power loss will depend upon the instant when the ignition occurs. So that's why not being instantaneous, it is the cause of the loss due to the ignition. So second loss we'll consider, that is due to heat conducted to the cylinder walls. So during the power stroke, the walls of the cylinder being cooler than the products of combustion inside, transfer of heat takes place to the walls and then to the atmosphere through the coolant. This results in power loss that is represented by the area 2 in the dotted line, this area in the diagram number 1. So that is due to the heat conducted to the cylinder wall. Then next loss is due to the exhaust valve opening not being instantaneous. So generally in this case, as it takes definite time for the exhaust valve to an actual engine to open and let out the exhaust gases, unlike theoretical air cycle where the exhaust is assumed to occur instantaneously at constant volume, power loss represented by the area 3, that is this area in this diagram number 1. Then next type of loss we will consider in terms of the pumping loss. We'll consider that some work is required to be done for inducting the fresh charge into the cylinder and exhausting the product of the combustion. This is called the pumping work, which is direct loss. As such, a finite difference of pressure is required both for the inflow of the charge as well as outflow of the exhaust gases. This results in the loss of the power represented by the area O in this diagram. So this represents the pumping losses. Then in the design of the carburetor and inlet manifold affect the flow of charge to the cylinder. So now we'll discuss about the fifth loss, that is due to the incomplete combustion. In theoretical calculations, it is assumed that fuel undergoes complete combustion in the cylinder to form carbon dioxide and water droplets or H2O. However, in actual practice, there is always incomplete combustion, as a result of which the energy in the fuel goes waste, due to which the losses occurred in an engine which affects the performance. Then next type of loss we consider, that is the friction losses. So some power is lost in an actual engine to overcome friction of its various running components or parts. Friction losses are caused mainly by the shearing of the lubricant film. Since no metal to metal contact can be allowed in the engine to avoid the wear, early wear. So these are some of the losses which affect the engine performance, as well as due to which output is also varied. So here now we will discuss about mean effective pressure, as it is mentioned that this is a hypothetical pressure. We are having one graph in between power as well as piston movement. So hypothetical pressure, which is if acting on the engine piston during one stroke, it would produce the total work of the cylinder. Then depending upon the indicated work or brake work, it may be indicated mean effective pressure, that is IMEP, or brake mean effective pressure, that is BMEP. That is mentioned here. IMEP, indicated mean effective pressure, is equal to IP over LAN. What is IP? IP is the indicated power. L is the length of the stroke. Small a is the total number of total piston cross-sectional area. Units are in meter square. And N, that is the number of working strokes per second. So this is IMEP, indicated mean effective pressure. Then we'll consider BMEP, that is the brake mean effective pressure, that will be BP over LAN. Here BP is brake power. So this graph is represented that variation in pressure with respect to the piston movement, that it may be indicated mean effective pressure, that is represented in this diagram, or it may be brake mean effective pressure. Let's discuss about the fuel consumption, that without fuel we cannot run the engine. So performance is based on the type of fuel and its consumption under a given test condition in a given time. It may be measured in terms of weight or volume. Specific fuel consumption, it is also mentioned as SFC, that is the specific fuel consumption. It is determined by dividing the total fuel consumption per hour divided by the power developed. So depending upon the value of the power used, that is with IP or BP, consumption is termed as the consumption. Here it is mentioned 2 times as indicated specific fuel consumption ISFC, or brake specific fuel consumption, that is mentioned in terms of BSFC. So now let's discuss about volumetric efficiency. Here for volumetric efficiency, one graph is represented. Volumetric efficiency against the engine speed, the variation in the efficiency shown with respect to the engine speed. So for a normally aspirated engine, it is defined as the ratio of volume of air or gaseous mixture inducted in a given time at a atmospheric conditions surrounding the engine to all the piston displacement of all induction strokes during the same time. So this is very important factor, that what atmospheric conditions are there, and for a supercharged engine, the volumetric efficiency, it is based on the temperature and pressure conditions in intake manifold. So these are the variables in this term of the supercharged engine. Then we can consider that volumetric efficiency, it depends upon the engine speed, then load, as well as the layout of inlet and exhaust system, the sizes of the parts, and valve timing. So this efficiency is totally dependent upon all these variables through which we can consider what output we will have after completion of the process. So in this we start the performance curve. In this video I will just introduce performance curve, but all the points of performance curves will be discussed in next video. So various engine output parameters are generally torque, then IP, that is indicated power, and BP, that is brake power. So here frictional power will be the difference of indicated power and brake power. So variation of various engine output parameters are mentioned here. Now the frictional power is the difference between IP and BP. As frictional power becomes a larger proportion of the indicated power with the increase of the speed, brake power curve drops more rapidly compared to the indicated power curve. So it is observed that engine speeds for maximum torque and for maximum power are not the same. Engine curves are always given for full throttle conditions, which rarely occur actually on the road. So for this lecture we will finish up to this point, but a similar point from performance curve will continue in the next lecture.